So let's jump right in. What you're looking at here, it's not just some dry technical diagram from a networking class. No way. Think of it as a blueprint. It's a blueprint for understanding our entire digital world and, maybe even for building yourself a brand new career in tech.
All right, so if we're going to navigate this map, we first got to get to know the city, right? So let's break this whole thing down into its most basic parts. We're going to explore the infrastructure of our digital city. Okay, first step, end devices. In our digital city, these are the homes, the offices, the coffee shops. They're the destinations. They're the starting point and the finish line for every single email you send, every video you stream, every website you visit. This is where the journey of data begins and ends. And we're talking about everything from your computer and laptop to servers and even those office phones that connect to the internet. Now, at the very heart of all this communication is this really simple but super powerful idea, the client-server model. It's a conversation. Your computer, that's the client, asks for something, let's say a web page. Then, some powerful computer on the other side of the world, that's the server, has that web page. And yep, it serves it right up to you. This constant back and forth, happening billions of times a second, is basically the fundamental conversation of the entire internet. So you might be wondering, how does your request actually get to that server? It's not like it just wanders around hoping for the best. Nope, it has guides. These are the intermediary devices. There are traffic cops, and they have two absolutely critical jobs. First, they act like little booster stations, giving the data signal a fresh kick of energy so it can travel really long distances without fading out. And second, and this is the really cool part, they're smart. They look at all the possible roads your data could take and pick the fastest, most efficient path at that precise moment. Okay, so we've got our destinations, and we've got our traffic cops. What about the roads that connect them all? That's what we call network media. This could be a physical copper cable, like your old phone line, a super fast fiber optic cable buried under the street, or just the invisible Wi-Fi signals flying through the air. And this is a huge deal for a network architect, because they have to pick the right kind of road for the job, always trying to balance stuff like distance, speed, the physical environment, and yeah, you guessed it, the cost. So what does that make the internet? Well, you can think of it as the ultimate WAN, the biggest, most complicated one imaginable. It's literally a global network of networks. It's all the world's LANs and all the world's WANs all hooked up together, speaking the same digital language so they can share information. It really is the ultimate digital city. And that brings us to a really important question. I mean, on the surface, this just looks like a simple lab exercise, right? Identify this, identify that. So why does it actually matter? What's the big deal? Well, the answer reveals a really powerful strategy for learning. If you could pull back the curtain and look at the physical structure of the internet, it would look like an infinitely complex transit system. Millions of pathways carrying a staggering volume of data requests, responses, and streams across the globe every single second. This blueprint is Cisco Packet Tracer Exercise 1.5.7, the foundational curriculum tool used to teach novices how to read digital maps. You start by looking at localized clusters like LAN 1 and LAN 2 at the bottom of the schematic. Translating this two-dimensional schematic into a mental map of active data pathways is the absolute baseline requirement for anyone attempting to manage real, physical global infrastructures. This chart outlines the curriculum's architectural anatomy, using a simulated environment to introduce enterprise-scale networks to novices. The explicit objectives require students to master technology identification by categorizing devices and media connections within the interface. This diagram shows a high-fidelity sandbox. The software acts as a protective barrier, separating student actions from real-world hardware. To learn networking, you inevitably break systems. Packet Tracer allows learners to explore without the risk of destroying physical enterprise equipment. Removing that physical and financial risk directly lowers the psychological barrier to entry. When a mistake costs $0, a learner stops hesitating and starts testing. By removing the threat of hardware failure, the sandbox allows students to prioritize troubleshooting logic over configuration fear, building the instincts required to work on live enterprise servers. This map outlines the four-phase cognitive progression of the lab. Phase 1 is unstructured exploration. The curriculum creates a period of low cognitive load, encouraging students to click around the interface without a specific technical goal. This diagram contrasts the lab's explicit academic directives against implicit pedagogical goals. By explicitly stating it isn't important to understand everything immediately,
The curriculum uses unstructured play to reduce tech intimidation, forcing students to independently investigate the environment. Before any student learns the technical rules of routing protocols, they must feel psychologically safe enough to navigate an unknown system and make mistakes. Once that psychological baseline is established, the lab pivots to Phase 2, strict visual categorization. Students must decode the digital map. This flowchart categorizes the 3 fundamental network building blocks. First, end devices, computers and servers originating data. Second, intermediary devices, routers and switches selecting the most efficient physical path. Third, media connections, the copper, fiber, or wireless roads carrying the traffic. This table maps the students' reflection questions against the conceptual competencies tested in Phase 3. By asking students to explain the client-server model, the curriculum ensures the learner grasps the invisible service logic dictating device interaction, moving beyond simple physical identification. In this phase, the student evaluates bandwidth limits, environmental constraints, and the routing logic required to keep a network functional. Recognizing individual components is only the first step. The curriculum immediately forces the learner to scale that understanding outward to encompass massive distributed environments. This table contrasts geographic network scopes. A LAN represents a contained neighborhood, like an office building. A WAN is the broad highway connecting these neighborhoods. The simulation presents the internet as a simple cloud, a necessary oversimplification hiding chaotic global routing to prevent overwhelming notices. Even with that simplification, the math is staggering. A single LAN with 3 computers and a switch scales exponentially when connected to a WAN, rapidly linking thousands of local nodes into a massive global network. The moment a learner comprehends this multiplication is the exact threshold where a local technician begins thinking like an enterprise architect. This diagram illustrates the applied challenge. Learners move from observing networks to actively building them. Step 1. Integrate an end device, selecting the right cable and IP configuration. Step 2. Intermediary expansion. The learner adds a router, deducing the required protocols. The final directive, constructing multiple interconnected LANs across a WAN entirely from scratch. This graphic maps how theoretical simulation on the left connects directly to real-world application on the right. The software actions in Packet Tracer physically translate to infrastructure layout and hardware standardization in live server rooms. The underlying lesson is systems thinking. The learner proves they understand that changing a single media connection or routing protocol alters the entire technological ecosystem. This funnel diagram demonstrates how the corporate job market evaluates these exact skills. Employers strictly filter candidates through baseline certifications, primarily the CCNA, to ensure they possess this specific foundational knowledge. This matrix connects lab skills to job roles. Identifying devices and applying client-server logic satisfies entry-level IT support requirements. Configuring routing devices and media connections qualifies candidates for mid-level network administrator roles. Generating new topologies from scratch establishes systems-level analysis for rapid career growth into network architecture. This roadmap traces the complete, uninterrupted trajectory. It begins the very first time a novice opens the Packet Tracer interface and extends directly up to a network engineer designing global enterprise strategies. Lab 1.5.7 provides the technical on-ramp for professional autonomy. By mastering the simulation, students acquire the architectural knowledge to manage live enterprise systems.
The reason I'm presenting this to the students is because I want you guys to start thinking bigger. I want you to start thinking about this career stuff now. With the onslaught of hearing a lot about AI, I want you to get really deep into understanding your career path.
In this particular lab, which is titled, of course, 1.5.7 Packet Tracer Network Representation, this particular lab is to teach you everything you need to know about packet tracers and how to use it and use the devices within here. Now, it's not going to give you everything like I just said. It's just going to give you the scope of how deep you can really learn how to use this particular device to better understand networks. So let's take a deep dive into it and just start breaking down some of the things. Now, I want you to understand all clients have full connectivity to the server. As you can see here, if you look at them, they pretty much are connected to the server. And I have it right here on this screen. One of the things I like to do when I'm working on a lab, I like to either have 2 monitors, or I like to just split it in half so I can see both of the devices. Most of you have learned how to do this and you do it. So that's kudos to you. So I just want you to know this is a better way of representing things. And you're going to get a chance to see me blow stuff up and shrink stuff down. And when I say blow up, I don't mean literally blow it up. I mean just make it bigger. So now this lab here has a network. This is not a real network. This is just something that's showing you how a network will look. So I don't want you to walk away thinking, oh, this is how everything is really. Networks are truly more complex and complicated networks out there. I mean, and if I can say that again, networks are really, really complicated. But this is a snapshot of what you will have to do. So for the sake of frame diversity, the environment is not entirely realistic, okay? If you think about it, for instance, net and pat overload on both networks. So let's go to the objectives. One of the things I also want to point out is, which I teach you in the class, is once you put your mouse pointer over anything, it can tell you the connections that you have in there on these devices. So make sure you do that just to see what type of connections. Like on this particular cell phone right here, and I'm gonna blow that up so you can see it better. On this particular cell phone, you can see if I come here and put my mouse pointer over here, it's gonna show you the gateway, the DNS server. It's gonna show you the IP address that's being issued out to that cell phone, or so you can see it's a lot of things going on in this particular network. So it says here, over here on the objectives, what is the objective? Remember, everything has a topology, everything has an objective, and we want to make sure we understand what we're doing in order to be able to do it. And you want to remember this. So our particular objective in this particular lab, or excuse me, packet tracing, the network model in this activity incorporates many of the technologies that you will master in your CCNA studies. It represents a simplified version of how small or to medium-sized business networks might look. So let's get clarity here. This is just giving you a bird's eye view of how a network will function. So just imagine, you just want to see what's going on within it. So feel free to explore the network at your own pace to learn as much as you possibly can. And if you complete the lab, go back and do it again just to make sure now that you have some knowledge, you can better do things. Okay, just a side note, in this particular lab, it says it is not important that you understand everything you see and do in this activity. So feel free to explore. Don't get caught up with saying, I want to make sure I understand it. Sometimes I have students that try to be so perfect in this that they tend to lose the point of it. The point of it is for exploration purposes. Let's say that again. Exploration purposes. It is to give you a bird's eye view of the things that you can do in here. So don't get stuck here, which you haven't. Now, identifying common components of a network as represented in the packet tracer. This is step one. So you just want to be able to take a look at the different components in here. So it says list intermediate device categories. How many intermediate devices do you see in here? Well, let's shrink the screen down and take a look. So as you can see right here, you have a plethora of intermediate devices in here. Just take a look at them. So if I wanted to know I have intermediate devices, I have what? I have routers. I can see 1, 2, 3 routers. I have switches. I have 1, 2, 3, 4, 5 switches. I have modems in there. I have wireless devices in here. I have LAN in here. So you see, you have a multitude of intermediate devices within your network. It's going to be up to you to demonstrate that you have that, okay? Now, also, it wants to know, without entering into the internet cloud or intranet cloud, how many icons in this topology represent endpoint devices. So you should be able to count out how many endpoint devices. Now, I'm only going to count a few of them. And I'm going to leave it up to you, which you already did, to tell me how many actual devices is. You may or may not have done this lab, but if you did, you probably already told me. But if you haven't, how many devices? Now remember, I am talking about the endpoint devices, okay? Okay, so not going into these intermediate or the cloud to count them. How many devices in here? Endpoint devices. Now, I'm not going to tell you the exact number, but let's say I go 1, 2, 3, 4, 5, 6. Okay, that's 6 I counted. I know that it's more than 6 in here. My expectation is that you will tell me the exact number. Okay, let's move forward with that. So you know what endpoint devices are. The next one asks this, without count of, so let's say we here it says we did the intermediate devices, we did the endpoint devices. Now it says here, without counting the 2 clouds, how many icons in the topology ref intermediate devices? Now I pretty much already told you that, but I'm not going to tell you the full number of the intermediate devices. What I'm going to do is count a few of them, but you got to tell me exactly how many in there. So if I look at an intermediate device, I go 1, 2, 3, and I'm going to leave it there because I want you to tell me the total number. So find out what an intermediate device is and tell me how many in there. The next one says, how many end devices are not, now remember, how many end devices are not desktop computers? Well, this looks like an end device right here. I'm going to blow that up for you so you can see it. So this looks like an end device to me, but it's not a computer, so I would count that. This looks like an end device to me, and it's not a computer, I count that. Even this looks like an end device, and it's a computer, but the question said this. The question said, how many are not desktops? Okay, so this is a laptop, it's not a desktop. So I can tell you right now, that's 1, that's 2, that's 3. What about this here? Can that be considered a end device? That's not a desktop. So I'm gonna let you tell me the exact number. I know the exact number, but I want you to do some work. And then the next question in this section, to close out this section, says, how many different types of media connections are used in this network? Now, I can see multiple media connections, and I can come down here and click on the connections to help me out. So I see this connection right here. If I come down here and move it over, that says serial. So I see a serial connection right there. That's 1. Then also I see these black cords, cables. What are they? I can come down here and move over and see that that's a copper straight through. As you can see, represented right down here, copper straight through. And I see them now. Now I'm gonna stop there. I just gave you 2 of them, but I know it's more. Okay, it's a lot more. So as your professor, I'm expecting you to tell me all of the end devices. Now there's one in here that will trick you up. So make sure you pay attention to your lessons. Remember the lecture I told you about. Okay, if you hear me drinking some, I'm drinking my coffee. You know this is morning time. Coffee, baby, coffee. Okay, let's move on. Okay, step 2 is just basically explain the purpose of the devices. So now this is when you get the chance to share your knowledge with me. This first question says, in Packet Tracer, only the server PT device can act as a server. Desktop or laptop PCs cannot act as servers. Based on your studies so far, explain the client-server model. You should be able to explain the client-server model to any IT manager. In our modern networks, a host can act as a client, a server, or both. Software installed on the host determines the role it plays on a network. You should be able to point that out. So if you think about it, if I put software on a desktop computer that's network software, I can turn that desktop computer into a server. Servers are hosts that have software installed that enables them to provide information and services. So just remember that I can take this PC and turn it into a server. I wouldn't do that. That wouldn't be wise. That would not be smart, but I can. But this is what a server is. A server issues out special software to the other devices so it can give them the services that they need. That's what I should. Clients are hosts that have software installed that enables them to request and display information obtained from the server. So these clients are reaching to this server. So that's one of the questions that I expect you to know. You should be able to go into any interview and explain what a server can do. Okay, so it says here, list at least 2 functions of intermediate devices. Maintain information about what pathways exist through the network and internetwork. You should be able to explain that to me. So it's multiple things you should be able to tell me, but I just need you to list 2 of them. Remember, just 2. Okay, and the next question is, list at least 2 criteria choosing the network media type. So why would you choose specific network media type? List at least 2 reasons why you would do that. So one, you could say the distance the media can successfully carry a signal. That's important. Let's say these 2 branch offices. This is the central office and this is the branch office. Well, what media would you choose to go from point A to point B? Okay. The environment in which the media is to be installed. What the environment. So why would I use fiber optics in this when I know that it'd be better to use coaxial or straight through? So just make sure you understand 2 definite reasons why you would do this. Remember, all this playing out for a reason so you can understand how these networks function and what's the purpose and the decisions why we make decisions to choose the different devices and medias that we use. The system checking out.